This is video 40 in our series Analytical Mechanics. The playlist for all the videos is at the website digital-university.org. Now in this video we're going to consider the same problem that we solved in video number 39, where it could be a billiard ball or it could be a bowling ball that has a linear velocity v0 and an angular velocity in the opposite sense, omega naught. So this could be a billiard ball that was struck below the center line by the cue stick, and immediately after that impact it has v0 and omega naught values. Or it could be a bowling ball that's thrown down onto the floor with a backward spin. And the question we answered in the last video was, if this just skids along the surface and then later just comes to a stop, what would have to be the relation between v0 and omega naught? And we're going to answer that same question in this video, only we're not going to use kinematics like we did before. We're going to use conservation of angular momentum. Now as the ball skids across the surface, there's a frictional force in this direction. This is positive and this is negative. Now let's see how we can answer the question, what's the relationship between v0 and omega naught if it just skids across the surface and then comes to a stop? So here's the setup. The ball is here, and it has an initial velocity v0, an initial angular velocity omega naught. It's skidding across the surface, and there's a frictional force in this direction. This is positive. This direction is negative. Now, in the last video, we started off by taking the torque about the center of mass. Let's do it in this video at the contact point, just where the ball makes contact with the surface. And in general, of course, the torque is the cross product of a position vector with a force. In this case, the position force is just friction. But what is the position vector? The position vector is supposed to go from the point of interest, C, to where the force is applied. But here the force of friction is acting right there at our point of interest, C. So the position vector is 0. So the torque is 0. So this tells us at point C, angular momentum is conserved. It's always a constant. And we know that because the time derivative of angular momentum equals the torque. But if the torque is 0, as it is in this case, then the derivative of the angular momentum is 0, which means the angular momentum itself is constant. So the angular momentum about point C is conserved. And we're going to consider it then at two instances of time. One will be angular momentum about point C, call it initially. That would be just after the cue ball is struck with the cue stick and it has v0, omega naught, or it could be a bowling ball just as soon as it makes contact with the surface that has these values here, v0 and omega naught. And then we're going to consider angular momentum final. But we're considering now a situation or a scenario where the ball skids across the surface and then stops. So that means the final angular momentum is 0. Well, if angular momentum is conserved, if it's always a constant, then that means the initial angular momentum, that too must be 0. Now here it's easy to understand why this is 0, because when it stops, V0 is 0, or V is 0, not V0, and the angular velocity, that also is 0, so obviously that's going to be 0. But here we have non-zero values, V0 and omega naught, initially. How can the angular momentum be 0 at this point in time? We know it must be because it is conserved. And the answer here lies in the fact that, as we discussed several times now in our previous videos, and we first, I think, showed it in video 19-C, that the angular momentum has two components to it. One is the angular momentum of the center of mass about our point of interest. Our point of interest here is C. So let's look at this in more detail. This has two components, two non-zero components. If it's going to be 0, then they must cancel each other. So the first component that is the angular momentum of the center of mass about point C. Now we know in general angular momentum is the cross product of a position vector with linear momentum. So here now we want to know, we're taking into account the angular momentum of the center of mass, which is right here, about point C. So we need a position vector. So we go from point C to the center of mass. So that position vector is just the radius of the ball. This cross MV0. So that is the angular momentum of the center of mass about point C. It's this cross product. And this is real easy to evaluate, obviously, because the radius here, R, and V0, they're perpendicular to each other. So this is just simply going to be R, M, V0. But is this a positive or a negative value? So let's look at it more closely. Here is R, the position vector, which is just the radius of the circle, and here is MV0. We don't draw it up here, though. We position the vectors in this way when we're taking a cross product. And then we want to wrap our fingers around this so that R is aligned with this vector. So to do that, we'd have to have it like this, and our thumb was pointing downward. So this component of the torque is pointing into the board, and notice when we're doing that, our fingers wrap around in this direction. And that's a positive direction. It is the counterclockwise, that is negative. So what this means is that the first component of the angular momentum about point C immediately, initially, that is when the ball, whether it's a billiard ball or the bowling ball, when it has these values, V0 and omega naught, that first component is just Rm V0. Now the second component that's always the same. That is the rotation, the angular momentum of rotation about the center of mass. And that is always the moment of inertia about the center of mass times the angular velocity. But now for our problem, the angular velocity is omega naught, and it's in this negative direction. So this is with a minus sign. So the angular momentum about point C, initially, that would be either immediately after the cue ball is struck with a cue stick, or a bowling ball first makes contact with the floor surface. It's this component plus this component. So this equals RMV naught minus this. And the moment of inertia, that is 2/5 R squared M times omega naught. So this is the angular momentum about point C. This contact point, if it's a billiard ball, it would be immediately after it was struck by the cue stick, or if it was a bowling ball, when it first makes contact with the floor surface, when it has a V naught and an omega naught. Now, when the ball comes to a complete stop, V and omega are 0, its angular momentum is 0, but that means then, at that point, if the angular momentum is 0, right here it must also be 0, because the angular momentum about point C is conserved, it's always a constant. So this must equal 0. And let's see what happens. This R cancels with one of these R's. This cancels, and we have V naught equals 2/5 R omega naught. And that is exactly the same equation that we derived in the previous video. So what this means is that we know that the ball has this initial velocity, or this initial angular momentum, this component plus this component. But if it comes to a complete stop at some point in time, then the final angular momentum is 0. But we know that the angular momentum about point C is a constant, so that means then that its initial angular momentum must also be 0. So we set up that equation, and here's what we get. So this tells us then that if we have a ball, a billiard ball or a bowling ball, whatever, and it has initial linear velocity in this direction, a backward angular velocity of omega naught, and an initial linear velocity V naught, if they have this relationship between them, then the ball is just simply going to skid across the surface, and eventually it will come to a stop. Okay, that's it for this video then. So here, this is exactly though what we derived in the previous video using kinematics. Now, what also can happen is if we have a ball, say a billiard ball, and it has a linear velocity, initial value V naught, and a backward spin to it, it can go forward and then come backward in pure roll. If it does that, what has to be the relationship between omega naught and V naught? That is what we'll consider in the next video.